Hi, I'm Professor Verkler, and this is Lecture 1-8 for ECE 1220 at the University of Utah. Today we will be talking about nodal voltages and ground. We are going to learn how to convert between voltage differences and nodal voltages. We're going to learn about earth ground and reference ground, and we're going to learn how to adjust nodal voltages when reference ground is moved. So if you remember from lecture 1, we learned that voltage is the potential difference measured between 2 points. One of the key things was we needed 2 points to measure a voltage difference. But wouldn't it be nice to just set a reference point so we don't have to keep referring to 2 points? Just like when we talk about elevation, we have a single number referenced to sea level. So we can do that with circuits, and we call that ground. So here's the symbol we use to represent our zero voltage reference point in a circuit. And there are other symbols besides just these two in the boxes. For example, sometimes you'll see the triangle without it filled in the middle, or there's something called chassis ground that looks kind of like this. So there are different ground symbols. And in certain subfields of electrical engineering, they may have special meanings, but for now, in this class, we will consider them all interchangeable, and I will generally use this one. Okay, so when we're drawing circuits like this that represent maybe this circuit built on a printed circuit board here, when I draw the ground symbol, I'm referring to reference ground. I'm saying this is the point I'm considering 0 volts when referencing any other node in the circuit. But there is also an actual thing called earth ground, which is the actual relative, I guess you could say, base point of voltage on Earth. Specifically, it's when we stick a metal pole several feet into the ground. That is the reference earth ground. And then we can talk about voltages in clouds or other places in reference to that point. So some examples of earth ground that you see around you every day would be this prong in your electrical outlets at home. So that should have a wire that's attached to piping or such in your house that then eventually goes underground. And so that's a path for current to flow kind of in an emergency in a circuit. Let's talk a little bit more about real-world examples of earth ground by talking about lightning. So if you remember, your textbook, the free downloadable one, has applications in it, and one of the applications talks about lightning rods and lightning. So I wanted to talk about that today. So we live in the beautiful mountains of Utah, and we get some pretty epic thunderstorms in summertime, and these big clouds roll in like this, and these clouds can have quite the charge built up in them to the point that the voltage difference between earth ground, right, that metal pole several feet into the ground, and the cloud can be over 1,000,000 volts difference. And so when there's such a buildup of voltage difference, at some point, the air will actually start conducting, and that is what creates lightning. So lightning is actually the air conducting some current down to earth from the cloud due to the giant voltage difference between the two. So let's talk a little bit about why lightning hits what it hits. So here's an example of a person on a horse in a field right here. So it turns out a person conducts more than the air does. So if lightning's coming nearby, it's going to naturally hit the person and travel through them because that's the path of least resistance compared to the air. Same thing with these trees over here, right? The lightning is going to hit the tree and go down through the tree, which provides a path of less resistance than going all the way through the air down to the meadow here. Down to the meadow. So that is why we use lightning rods. It's for the same exact reason. So I think down here, yes, I have a picture of a lightning rod. So the idea is the lightning rod is the tallest point on the house, and it's a piece of metal which easily conducts. And so then the lightning is going to want to hit that piece of metal and take the path of no resistance down that piece of metal wire down into the earth. And so this may save electronics or other electric circuitry in your house by having a lightning rod. I think my dad actually had his satellite dish hit by lightning a year or two ago, and it destroyed all the electronics attached to the satellite dish. Okay, so now let's talk about how to actually apply this idea of nodal voltages. So before, we were always talking about voltage differences, right? We'd label a plus and a negative to show where we were comparing the voltage between. And now what we're going to do instead is on the same circuit, we're going to draw a ground symbol somewhere, which says this is the 0 voltage point for reference. And then because we know there's 1.5 volts across this device, right, across this voltage source in parallel here, then we know the nodal voltage up here is 1.5 volts higher than the reference ground. So we can say this whole node has a voltage of 1.5 volts compared to ground. So now instead of having to label a positive and a negative, which represents a voltage difference, we can just label nodes with voltages referenced to the ground point. So let's do that on a worked example here. So I can put a ground at any node I want. Some may be more sensible locations than others. So in this case, we have 4 nodes. So I could put a ground here, I could put a ground here, I could put a ground here, or I could put a ground down here. So in a circuit like this, with just a single source, the 12-volt voltage source, and a bunch of resistors, it turns out that we only get voltage drops across the resistors. And so the lowest voltage in the circuit comparatively must be the negative side of the battery down here. And so if I choose to put the ground here, that means that actually all my voltages in this particular circuit will be positive, which I like. So to me, that is a sensible place to put it. So a lot of times when you just have a single source in a circuit, you will put the ground at the negative terminal of that source. So I'll erase these other locations for now. Okay, now let's talk about how we label the other nodal voltages. So we immediately, because this is the reference node, we know this is 0 volts. And then we can trace from here and use the voltage differences to figure out the other nodal voltages. So here, if I trace up through the voltage source, then I see that I go up 12 volts to get to this node. So this node is 12 volts compared to ground. If I keep tracing this way, right, I come out this side, I subtracted 2 volts with that voltage difference. So this node must be at 10 volts. I can similarly trace up this direction, right? So I added 6 volts according to that voltage difference. So this node must be at 6 volts. And then we can kind of do a sanity check here at the end and make sure that our nodal voltages match the voltage difference here. So to get a voltage difference, you take the voltage, the nodal voltage at the positive side, and then you subtract the nodal voltage over here at the negative side. So 10 minus 6 gives 4 volts, and that's indeed what the voltage difference is labeled. So therefore, all our answers are self-consistent here. Let's do this one more time now, but let's move the ground. So now I've put the ground up here. So this is 0 volts. So tracing through this way, climb out the negative side with that voltage difference. So this must be negative 4 volts over here. So notice now by moving that ground, I have negative voltages in my nodal voltages in my circuit. If I trace this other way from 0 plus 2, then this nodal voltage must be 2 volts. And then if I keep tracing this way from negative 4, so I start with the value negative 4, and then I subtract off that voltage difference, so minus 6 volts, which gives me negative 10 volts. So this must be sitting at negative 10 volts down here. And then for a sanity check, let's finish going around the loop here. Negative 10 plus the voltage difference of 12 volts of that voltage source gives me 2 volts, which indeed is what the nodal voltage is labeled at the top left. So therefore, our answers are self-consistent. And one thing you should actually notice here is that because all the voltage differences stay the same, and I've just changed where I'm labeling the reference point, is you should see that all of these nodal voltages are just shifted by the same value. So up here in this circuit, right, this node was 10 volts, and this node was 0 volts, but then we made the 10 volt node ground or 0 volts, so it's like we subtracted 10 from the reference of every nodal voltage. So before in the upper right we had 6 minus 10, we end up at -4. And for the upper left, when we started at 12, subtract that constant 10 off, and we ended up at 2 volts. So all these nodal voltages have the same differences between them comparatively, and they've all just shifted absolutely by 10 volts. Okay. The final thing I want to talk about is what I call power rail notation. So previously, we've always drawn our circuits kind of as a loop with a voltage source. So you'll see now that some people will start leaving off the voltage source, and instead, for the positive side of the battery, they'll draw it like this. And then they'll put a ground symbol at the negative side of the battery. And this kind of makes sense in light of our breadboards, because we were taught that we can use these rails on the side as power rails. And so this one's your ground down here. And this one up here is the plus 9 volts, I guess, in this case, since we have a 9 volt battery here. And then you build your circuit here in the middle. And so what's important to notice with this kind of a notation is we don't show the full circuit loop here, which means we don't show the full path that current follows in a circle. So that's something you're going to have to implicitly remember in your head, is that current is indeed flowing in a loop. It's flowing out the positive side of the battery, through the circuit, and then back through the ground in a loop through that voltage source that is no longer drawn directly on the picture in this power rail notation. And with that, I think you have all the knowledge you need to be able to do worksheet 1-8. So go and attempt that worksheet now.